Last time we were discussing about the economic analysis. The ultimate objective has been, after evaluating the performance of solar energy systems on long term basis, we couple it with the economic analysis. A simple issue is about this savings method or the payback period, which we have indicated by the simplest possible thing, whatever is the fuel cost saved in the first year to the investment, it may require a few years to recover the investment, though it is a simplistic calculation. Now, we shall go a little detailed about the so called life cycle savings method, the P1 P2 method. That means, the life cycle savings are calculated based upon two parameters, P1 and P2. In general, the basic idea of the method is all the expenses on account of installing the solar system has to be taken into account and calculate all the savings. Take into account economic scenario, fuel prices, inflation and depreciation and performance degradation if possible in evaluating the above. Similarly, when you have installed the solar energy system, there will be certain expenses which may involve the principal and interest paid on the total investment needed to install the solar energy system and the auxiliary power cost. So, let us say installments and the auxiliary power. In addition, there will be certain maintenance cost, even cleaning the solar collectors, and that may include the labor also. And mainly the savings come from fuel cost, what is the fuel it saved, and there could be tax benefits, because this is a green investment. There are tax benefits given by the government in various countries, and then government incentives, if any. In other words, there may be a subsidy in that, and there may be additional benefits by the government by installing, if you install a solar energy system and do not use the conventional fuel. So, in general, the life cycle savings, as we have explained, the amount of money that the system is going to save to the earner during the lifetime of the solar energy system, we will call it the life cycle savings. So, the calculation of this is an involved process, because the fuel prices do not remain constant, the interest rates may not remain constant, auxiliary power rate may not remain constant. So, all these features have to be taken into account, of course, assuming a certain scenario. And these features have been accounted by Brandmühl and Beckman. The reference will be given, is available in your companion notes. So, this is commonly known as the life cycle savings analysis. Short form LCS analysis. And of course, as we had pointed out earlier, a system is considered economically viable if LCS is positive and not viable if LCS is negative. So, if you maximize the life cycle savings, in the sense when it is positive, it will lead to some sort of a optimum configuration for the system under consideration. So, now we split the total cost of the system C s as comprising of an area dependent cost C A times A C plus an area independent cost. In other words, if a collector area is taken into account, if 100 square meters are there, it should be 100 multiplied by something, and if it is 200, it will be 200 multiplied by something. So, for each collector you may also associate a certain amount of piping, certain amount of platform, certain amount of stands or whatever are necessary. So, you can put all those things in this factor C A, which depend upon the area of the collector, and in addition this C E may be coming from heat exchanger and maybe to some extent storage tank, though that is also proportional to the uh, collector size, and then pumps, etc. So, unless the size drastically changes, the pump and the heat exchanger and the storage tank do not change directly in proportion to the cost of the area of the collector. So, C s is a m x plus c type of equation, where C A is the cost per unit area of the collector involved and C is a fixed cost, which is independent of the area. So, this C A could be R s per meter square and C E is simply rupees. So, Brandmühl and Beckman, they said all income and expenses which are necessary to evaluate the economic viability of the system are characterized by two parameters, P 1 and P 2. So, P 1, if you want to have an idea before we try to calculate that, is the ratio of the life cycle fuel cost savings to the first year fuel cost savings. So, in other words, this P 1 will take into account how the fuel prices are going to change over the life cycle of the solar energy system, and P 2 similarly is sort of a indicator of the expenses, is the ratio of life cycle expenditure incurred because of installing the solar energy system So, is the ratio of life cycle expenditures incurred because of the additional capital investment to the initial investment. So, you may make a down payment 100% or 80% or 10%, and there will be several things like depreciation of the system, inflation, etc., etc. So, all costs proportional to the first year fuel costs are included in P 1. All costs proportional to the first year fuel costs. This is just to make you appreciate before you go for a formula to calculate the P1 and P2s. Basically, P1 is going to indicate how much you are going to save. Okay? So, all that should be proportional to the first year fuel costs according to the economic scenario. Then any costs that are proportional to the investment are included in P2. To the investment are included. So, you may make a down payment of 10%. If the investment is larger, the 10% will be larger. If the depreciation is more, the final value will be less. If the inflation of the system is higher, my final value will be higher. They are all included in P2. So, life cycle savings is simply given by the parameter P1 CF times load and the load fraction F minus P2 times CA AC plus CA. So, basically if you forget about P1 and P2, it is almost like that simplistic payback period calculation. Life cycle savings will be the cost of the fuel in the first year multiplied by the load fraction to the solar load fraction, load into the load fraction, that will give you the energy delivered. So, this is the amount of fuel money saved in the first year minus the cost of the system. Okay. And CF is the cost of the conventional energy which could be Rs per gigajoule. So, how do we optimize AC or system? Such that at the chosen or arrived at AC, LCS is a maximum. You recall, so far we have not said how to calculate P1 and P2. However, sufficient indication is given that life cycle savings can be written in terms of P1 and the cost of the fuel in the first year multiplied by the energy delivered in the first year minus the cost of the system multiplied by an appropriate factor, right. So, this will be optimum will be delta by delta AC of LCS should be equal to 0, which will be P1 CF L times dF by dAC minus P2 CA, right, because that is a AC that differentiated with respect to the area that goes off and the fixed cost does not give anything. So, from this you can find out dF by dAC will be P2 CA upon P1 CFL. So, if the slope of the solar load fraction with respect to area equal to P2 CA upon P1 CFL, that point will represent either a maximum or a minimum. In the present context, it will be a maximum. One can easily verify that if you divide this or rather second differentiate it, it will be negative or just equal to 0. So, now we have briefly indicated about the life cycle savings curve. This is the area AC and this is LCS positive and negative, and this is area versus F curve. This should be the optimum, that is where you have your LCS maximum. So, if you draw a line with slope equal to, of course, df by dAc is P2 Ca by P1 CFL. So, you know this number, having calculated P1 and P2, Ca is known, Cf is known, L is known. Okay. So, you will find out this number and draw a line with the slope being equal to this number, and wherever it cuts, of course, I have drawn it little away just to be clear. So, that is where my optimum F and AC lie. So, the idea of the analysis is that you find out that the life cycle savings is a maximum where your load fraction delivered need not be 100%, but the returns per rupee investment is the maximum. Okay. So, that is how now you understand the importance of the solar load fraction versus the area curve for the long term performance, and that we have struggled through a large number of equations and methods to find out F versus AC curve. That combined with the life cycle savings will yield what should be the optimum for the particular system or application under consideration. Now, let us try to have an idea of how to calculate this P1 and P2. So, this is a bit of economics, and you just listen carefully, and then you can go through these slides in detail and then work out for yourself. So, all costs proportional to the first year fuel costs are in P1, and similarly any cost proportional to the investment is in P2, and P1 and P2 are defined by P1 is equal to 1 minus C T bar times PWF NE I D. Let me explain where C is a flag C equal to 0 if the property is non-income producing. In other words, we are distinguishing, even if it is a solar energy hot water system, if it is used for domestically for bathing or cleaning the dishes, it is non-income producing. But if it is used for degreasing or in any automobile industry or any other industry, it will be considered as income producing, and C should be equal to 1 if the property is income producing. In other words, if simply if C is equal to 0, it present worth factor of any ID is nothing but P 1. So, and of course, PWF is the present worth factor, which will depend upon any the term of the economic analysis. It may be 10 years, it may be 20 years, it may be 15 years or 5 years, like that. It could be ideally the life of the solar energy system, but in case you are not sure, you would like to see whether the life cycle savings are positive or not, and when positive, what is the minimum NE that could be required. IF is the fuel inflation rate. So, the fuel prices may be going up at the rate of 10%, 5% or whatever. So, you definitely compare it to the first year fuel savings to the total fuel savings will depend upon what is IF, and D is the discount rate. This is a delicate thing to understand, and one would think that IF is equal to D, but IF in the context of the present analysis is the fuel inflation rate. It is the inflation rate of the fuel only, not the overall inflation rate. This discount rate D is if you want to have, say, Rs 5,000 in 2015, what you should invest in a bank or anywhere today in let us say 2012. So, you want to have 5,000 rupees 3 years later from today. So, there is 5,000 rupees is discounted and it becomes 3,832, whatever is the number in 2012 terms of money. Okay? So, if there is a good chance that the inflation rate and the discount rate are equal, and in general it should be the same if you are talking about overall discount rate and overall inflation rate, but since you are talking only about the fuel inflation and the discount rate in general, so these things will differ in calculating your P 1 and P 2. Now, P 2, you have a long expression. So, I think this should be focused a little longer. D plus 1 minus D and present worth of N minimum 0 D upon present worth of NL 0 M times minus 1 minus D into T bar, and this multiplied by present worth of n minimum m d times m minus 1 by PWF of NL 0 m. You do not have to be scared about this long expression, because only thing that is dangerous is that present worth factor. Fortunately, there are websites given that n minimum or whatever the next number and the d, it will calculate and tell you the present worth factor straight away. So, of course, I will give the formula too, but this looks like an enigma because you do not know the economic term, the present worth factor, which simply means if 1000 rupees are to be spent after 10 years, what is the present worth of that? Plus 1 minus C t bar times M s into present worth factor of N e I d plus t, not t bar, 1 minus t bar times V into present worth factor of N e I comma d minus C t bar. This I am writing. I suppose you will be able to see it from your screens while I am writing, or the typed version and min dashed, or you can refer to Brandmühl and Beckman's original paper, which I have given the reference, or the textbook by Duffy and Beckman. So, this is available, and you make sure that the expression that you are using is correct, rather I am writing is correct. So, this is a lengthy expression, and each symbol has got a meaning, has got a explanation. M, annual mortgage interest rate. These terms, those who are not familiar with a lot of economics may sound unfamiliar, but you can easily go to Wikipedia and then try to have a understanding, because my whole objective here is to say that there are rational methods to evaluate the economic viability, rather than a hand waving approach. Okay, 2 years, it is fine, right? Instead of that, you can actually calculate depending upon the economic scenario of the country, the location, depending upon the application. So, NL is the term of loan and minimum years over which mortgage payments contribute to the analysis. Actually, it will be the minimum of NE, NL, right, which we have already defined. ND is the depreciation time in years. Then you also have a n min dashed, right? Yes, that is the last but one term in the previous expression. Years over which mortgage payments contribute to the analysis. This is minimum of NE or ND. Okay? So, it is n minimum and n minimum dash are the same. In one expression we use the minimum of NE or NL, and in the other expression minimum of NE or ND. Okay? Either depreciation or the economic term, depreciation or the term of loan. Okay? They all in principle can be different. So, if NE turns out to be the minimum, n minimum will be equal to n minimum dashed. T is the property rate on assessed value. And D is the ratio of down payment initial investment. So, some of these terms look unfamiliar because as students or as youngsters you may not be dealing, and some of them are even unfamiliar to me too until I try to find out. Suppose a house is going to cost about 32 lakhs in India, right, and then you may be paying through equalized monthly installments to the bank or to the whoever has given you the loan, but then there may be a 10% down payment. So, you may pay 3.2 lakhs initially and then the rest in terms of installments. So, D is a ratio of down payment to the initial investment, whether or not you have really actually put in that money. So, in other words, the commitment for the investment is so much, out of which you paid a certain percentage as the down payment. That is called the down payment. And MS is the ratio of first year miscellaneous costs This could include auxiliary power, maintenance, etc. to initial investment. So, this in a way is going to tell you out of 32 lakhs or 40 lakhs whatever you have invested on the solar energy system or in general anything, you need the ratio of the first year miscellaneous cost to initial investments. In other words, if it is a large property, probably your first year cost will be also higher, and if it is a small property, it will be less. And the V is the ratio of assessed valuation of the solar energy system in first year to the initial investment in the system. So, assessed valuation of the solar energy system in first year to the initial investment in the system. So, you may not pay all the amount. So, there is a particular ratio. So, because that is going to decide how many installments you will pay, how much you will pay over how many years, and consequently your present worth factors, etc., etc. RV is the ratio of resale value at end of period of analysis to initial investment. So, this could be a factor 1, less than 1, or even more than 1 if the inflation is high. So, one has to find out if the RV is higher, it is a better system. In general, the economic viability will become better and better. Now, in general, present worth factor over a period n with inflation rate I and a depreciation rate D, right. It depends upon 3 parameters. Is calculated from sigma j is equal to 1 to n, that is the total number of events 1 plus I to the power j minus 1 by 1 plus d to the power j times 1 by d minus I 1 minus 1 plus I by 1 plus d to the power n if I is not equal to d. So, this should be equal to, and simply n by 1 plus I if I is equal to d, right. So, if I is equal to d, this will be a d, this will be a d, j minus 1 by j, it will be 1 by 1 plus d summed over 1 to n will be n by 1 plus I or 1 plus d. Okay. So, 1 by d minus I into 1 minus 1 plus I by 1 plus d to the power n, that is the same thing which we are written in terms of n, and this is summed up over this period. N is the number of payments which may be your number of years of analysis, and I is the inflation rate, and D the discount rate. So, as I was pointing out, the inflation rate and discount rate could be similar order of magnitude at least. That is borne out by the fact that this present worth factor is given if phi is equal to d and if I is not equal to d. Now, I am sure still these terms will be a little unfamiliar to you. So, you go through them a good number of times and you can see a very good references even in Wikipedia and another website edgesdesigner.com, and where you have even the so called calculators. Just you give I, D, N, it will tell you your present worth factor of the quantity that you are looking for, and then you make sure your calculation is correct. Okay. So, we made that simple payback period calculation in the last class, and however, I was not very happy with that coal having a payback period of some 37 years or so. And then I realized that the price is at the pit head of the coal mine as per the website of Coal India. So, consequently, considerable transportation cost is involved, and I inquired locally and the rate changed quite a bit. So, I thought let me compare the coal, LPG and the electricity relatively by the simplest method of this one. So, the first year savings at the rate of 16 gigajoules per month for 12 months at a solar load fraction of 0.6 will turn out to be 115.2 gigajoules. These are consistent numbers, only thing is I am doing it only for 1 year, so that my payback period is the total upon the 1 year cost or savings. And if you assume a 80% efficiency for both LPG and coal based system, coal saved 115.2 by the calorific value in gigajoules 0.023 into the efficiency, which is 80%. That will be 6261 kilograms. And LPG saved will be 115.2 upon 0.04 gigajoules, that is the calorific value, multiplied by 0.8, the efficiency will be 3600 kilograms. Electric energy saved so efficiency is equal to 80% in those two cases. At this will be little higher, which will be equal to, it is 12 kilowatts for 12 hours a day multiplied by 365 multiplied by the solar load fraction 0.6 by efficiency 0.9. This will be equal to 35040 kilowatt hours. And we already estimated system cost at Rs 8000 per meter square for 50 square meters will be Rs 4 lakhs. Okay. So, in a simple form of table I have shown here the fuel, and at the rate of savings first year and payback period. In years. So, first one is coal at 1.1 rupee 70 paisa is too low a value, 3 per kg. This comes to about Rs 18,783, leading to 21 years, and at Rs 6 per kg, this comes to double 37,566. This becomes half, 10.5 years, and Rs 10 a kg, which will be Rs 62,616, leading to 6.3 years. These are not cooked up numbers, and I have locally verified that the coal, just household coal, is sold at about rupees 10 per kg. So, 6.3 years, still it is a large time if you compare with the coal. This is about 450 rupees. Of course, there is a recent hike for first 6 cylinders and the next 7th and onwards. I do not know whether it will be the 6th one or the subsequent one. So, I took 35 rupees a kg, and this will come to Rs 1,26,000, and this comes to 3.17 years, quite reasonable. Electricity, this is where we had little bit of confusion. So, if you take at the lowest spectrum, rupees 3 per kilowatt hour, this comes to Rs 105,120, that comes to 3.8 years. And if you take in the domestic bills I have verified, it varies from 2.75, 2 rupees 75 paisa to 7 rupees or so, depending upon the block. And if somebody is using a electric geyser, we will definitely be in that higher range. This comes to 1.9 years. The numbers, I do not say they are unimportant, but what we are trying to essentially imply is that the viability of the solar energy system will depend upon with what source of energy you are comparing, right. And if you go to wood, charcoal, or the wood picked up by in India by poor people who sell it maybe at a rupee a kg or even less, then if you compare that heating or with any solar or electrical, that will be highly looks uneconomical, but this seems to be okay. And these are definitely, with respect to electricity, it should be somewhere in between, even LPG 3 years. So, again I am assuming inflation and depreciation, these costs may cancel each other, and this is a fairly indicative of the actual accrued savings or the payback period. Okay. So, we shall consider the other important things, having done this economic analysis. In our curriculum we have got the passive systems, and that is what we shall do in the next lecture. Thank you.